Howdy, y'all, and welcome back to the channel. I've been in or around the flat Earth debate for 4 years now, thereabouts. In the comments section, and also appearing on streams. I actually have a few streams myself where I discuss the subject with those who profess to believe that the Earth is flat. But I don't really make content in direct response to that. However, I feel that I need to address something. And I think it goes to an overall, larger theme that really needs to be discussed amongst debunkers and people who want to properly communicate science. The core of it, well, the impetus of this is the apparently age-old question: is gravity a force? Nope, it isn't. It just isn't. The rationale that some people have put forward is that the flat Earth needs gravity to not be a force in order for the flat Earth to exist, mainly for the Earth not to be able to be a sphere. But I think there's a subtle difference here. This is what I would like to know from folks like Raichi, is agreeing that gravity is not a force. Does that also equate to you that gravity does not exist? Because the two are mutually or not mutually exclusive. Gravity not being a force does not mean that gravity as an effect, as an aspect of reality, doesn't exist. Now let's talk about gravity as a force. Gravity was first described as a force by Isaac Newton. F equals ma, 3 laws of motion, yada yada. Unfortunately, but this idea, Newton's idea, or more broadly, the more flushed out version of what we now know as classical mechanics, is not consistent with general relativity when it comes to its fundamental basics. For instance, classical mechanics will tell us that space and time are two separate variables, or there are two separate ideas, they are two separate properties that can change irrespective of each other. General relativity tells us that's not actually the case. The two of them are intrinsically linked together. If you change one, you're going to change the other. Classical mechanics also tells us that an absolute frame of reference can exist, that absolute position, absolute time can exist in the universe. General relativity, on the other hand, says this is impossible. There is no such thing as an absolute frame. There is no such thing as absolute time. And then I could go on for an entire lecture about geometries and other things that general relativity brings into the argument, or brings into light, rather, that are not reconcilable with classical mechanics. Now, you might be asking me, Professor Parks, if that's the case, then why do you have a classical mechanics book sitting on your desk? Why did you study classical mechanics both as an undergraduate and a graduate? Well, that's an excellent question, hypothetical person. And the reason for that is really the core of what I want to get to. And that is the difference between perception or perspective, and not in the typical way that it's been used in the flat Earth conversation. Perspective and reality. In reality, gravity is not a force. In reality, gravity is a consequence of the curvature of space-time. Mass dictates how space-time curves, and in turn, the curvature of space-time will then affect, or will then communicate to another mass, how that mass will move in relation to that original mass. So that is the reality of it. In practice, however, when we talk about the applications of classical mechanics, when we talk about the motion of objects in our terrestrial regime. And even as an astronomer, I can say that we use classical mechanics when dealing with stars orbiting around the centers of galaxies. We use classical mechanics all the time. The reason for that, the reason why it's still applicable, is because of our acceptance of precision. We are limited by the technology at hand. That means we are limited by the precision of those instruments. They can only measure a real effect down to a certain level. When we talk about stars going around other galaxies, or books dropping on the table, or pedantic idiots dropping microphones onto a stage, in each of those cases, if you're going to do a measurement or if you're going to do a prediction, then in terms of the precision involved, the effects of general relativity are negligible. They are there in reality, but they are negligible and can be dismissed. An analogy that I'd like to use is a harmonic oscillator. In classical mechanics, there's an entire chapter dedicated to simple harmonic oscillators. Does such a thing exist in reality? No. Nothing in reality is a simple harmonic oscillator. However, for instance, a pendulum can be considered a simple pendulum if you do not displace the weight more than 20 degrees off equilibrium. In that case, you can describe that motion within the precisions of instruments, and usually within the precision of what you want done, very well by a simple harmonic oscillator. Does that make the pendulum a simple harmonic oscillator? In fact, in reality? No, it does not. The small angle theorem does not get rid of the sine function. It does not negate trigonometry. It simply means that measuring the sine angle will give you the exact same, will give you an amount, or give you an answer that is so similar to simply just taking the angle that the decimals at the far end don't affect you, but will not affect the precision of your observations or your measurements. This is why significant figures exist. In other words, our technology typically limits us to significant figures that do not delve or do not reach into the precision that, say, a general relativity treatment will be needed, or will be seen, rather. And in other cases, even if the technology were there, we don't care. If I'm sure that if civic engineers, hi Norm, are out there and they're building something, they're not going to go through an entire GR treatment to figure out the stress on a load-bearing object, when classical mechanics is perfectly fine given the constraints, or given the, what's the word I'm looking for, the tolerances of what that load-bearing structure has to bear. But again, I want to stress that it's not what it actually is. It is a useful tool. It is a useful approximation. And physicists do this all the time. I have often worked, not often, but I have worked in the past with treatments of stars, looking at the hydrodynamics of stars, essentially what is the interior chemistry of the star, what is the density, the pressures, the temperatures, as a function of radius coming outward. And in many cases, actually in all cases, you have to treat it with some sort of approximation. We like to treat things as spherical cows. And as much as we would love them to be spherical cows, stars aren't. And in some cases, stars are very much not spherical. They are quite oblong, which is really awesome. I would check it out. Star Altair. If you Google on Wikipedia, one of my colleagues, Fabian Baron, was able to actually image the the surface of the star of Altair, and it is rugby shaped. Anyway, I digress. Physicists and astronomers use the approximation of a spherical cow all the time. Flat Earth proponents have often used manuals from NASA or the Army or what have you that says that in the first few chapters or first few sections, they will say, we are treating the Earth as a flat, non-rotating structure. Okay, that is what we call a good first approximation. Meaning that if your precision is not very high, if you don't care whether or not that artillery shell hits within 500 miles of your target, then sure, treat it as a flat, stationary, non-rotating object. But if you want to knock the wings off a fly at 5,000 yards, you're going to have to take Coriolis into effect. So it really just depends on what your perception is. What is your tolerance of what you can see, what you can experience? Another thing that has been brought up, and I think this also ties to it, is whether or not the Earth is a perfect horizontal plane or what have you. And on a local extent, yes, it is. Therefore, we can use elevation angles, we can calculate altitudes, and so forth and so on. Because locally, within the precision of our instruments, within the precision of what we can measure in terms of altitude or elevation or what have you, that is a fine approximation. Now, as technology evolves and potentially our needs evolve, then that approximation may no longer be applicable. So, again, treating something as a thing is different than the reality of that thing. So, gravity is not a force in reality. It just isn't. By definition, essentially. It doesn't travel instantaneously. It does not have a carrier particle to communicate what one mass wants to do to another mass. It just simply isn't a force. It is curvature space-time. However, we can approximate the effects of gravity if by treating it as a force. And I think that is a vital distinction that needs to be made in these conversations. Because I don't think that's fully appreciated among those who hold on to the flat Earth belief. Because, frankly, the first thing out of their mouths, if you were to encounter one, is, why do you believe the Earth is flat? They will typically say, well, look around you. Do you see curvature? Do you see anything other than flat? Obviously, hills and stuff, or ignore hills and mountains and stuff. But do you see curvature? Do you see the Earth sloping away from us? No, you don't. Because our human eye isn't capable of measuring or perceiving the curvature on such large scales. Even simple measuring instruments can have difficulty measuring that. Although I've been told that if you use some kind of auto level with a measuring rod or something like that, you can do a great job of measuring the curvature in or around the Blackpool Tower area of England. But again, I digress. The point that I'm really trying to hammer home is that as science communicators, which I believe debunkers truly are, is we don't want to fall into the trap of what we say, to flurf you've got to lie. Flurfers got to lie to flurf. Because they will often misrepresent things. We cannot do the same. If we want to be effective science communicators, we need to be clear about what is and what isn't reality, and then conversely, what is and what isn't an acceptable approximation for determining the motion of things, or the heights of things, or things of that nature. So, I think that was really all I wanted to get off my chest today. If you want to have a discussion about the nuances of gravity being force in the context of being an emergent force, such as the Coriolis effect or centrifugal force, I will be happy to have that conversation with you. Although I think it's more of a semantic one than anything else. And feel free to drop comments in the comment section, challenging my position on this. I welcome comments. I welcome conversation. I will explain my point of view as well as I can, and we can move on from there. Because unless we can communicate effectively, unless we can have these conversations, and this is a life lesson that goes beyond flat Earth or what have you, is if we want to be able to communicate with each other as human beings, if we want to reconcile differences, whatever that difference may be, we need to have calm, consistent conversations. We need to have conversations that are honest and that are well-meaning. We have to be open to the idea that we can be wrong. I don't believe at this point that I am, but I'm having a conversation with a webcam. If I have a conversation with someone else, maybe that'll change. I'm open to ideas. Oh, before I go, QE, if you're watching this or one of your followers are watching this, pressure is not a force, man. Flatzoid, pressure is not a force. In the same way that velocity isn't a displacement. Voltage isn't a current. Now, I suspect what you're trying to do is misrepresent that when I say that, or have said in the past, that pressure is not a force, that I am stating that a force isn't present at all, or that pressure has nothing to do with force. And that isn't the case, obviously. Pressure is equal to force divided by acceleration. You have to, I know that's going to be clipped. Pressure, let me state that again. Pressure equals force divided by area. That's right. Hopefully, I don't get misrepresented with that. That area is important. That per unit area is important. It's vital. Because, again, if you don't include it, you're misrepresenting reality. All right. With that, peace out. Have a great day. I'm hoping to be able to put out, in addition to my cosmology lectures, I'm hoping to be able to put out talking about whether or not JWST actually debunked the Big Bang. I'm hoping to stream on Sunday morning for Coffee and Science to bring that back to address that same question, because it's an excellent example of how miscommunication in science can happen and can become mainstream, because this idea that JWST debunked the Big Bang was propagated by mainstream outlets because, hey, it's clickbait worthy. So stay tuned for that. Hopefully I can get my things together to actually do that this Sunday. All right, again, peace out.